그럼 제3회 수소의 날 글로벌 포럼 오후 세션을 시작하도록 하겠습니다. 이번 시간에는 글로벌 청정수소 생태계 구축 방안에 대한 발표를 듣고 또 좀 더 심도 있는 패널 토의를 하는 시간을 가져보도록 할 텐데요. 먼저 첫 번째 발표자를 무대 위로 모셔보도록 하겠습니다. 첫 번째 발표로 IPH 로랑 안토니 사무국장님께서 수고를 해주시겠습니다. First, ladies and gentlemen, please allow me to invite Executive Director Laurent Antony of IPHE to the stage. 여러분 큰 박수로 맞이해 주시기 바랍니다.
Good afternoon, ladies and gentlemen. It's a real pleasure to be here. And first, I would like to thank the organizers for inviting me and giving me the opportunity to participate to this first session. So my talk today will be on hydrogen certification and the importance of mutual recognition of these hydrogen certifications. So as mentioned, I am Laurent Antony, the Executive Director of the IPHE. And IPHE is a government-to-government partnership, as you can see here, which aims at really develop and accelerate the deployments of hydrogen and fuel cells. And we are now 24 members all around the world, created 21 years ago, and you see Korea is also one of the founding members, and currently chaired by South Africa with Vice Chair the US, Japan, and the Netherlands. And IPHE is really here to discuss at governmental level about policies, strategies, also to share about initiatives, demonstration, and to monitor what's going on in hydrogen domain. And after to see how international collaboration could bring added value to make it happen faster. And of course, we're also working with many other initiatives in order to be as inclusive, either on the public side with other public initiatives, or also with the private side in particular the Hydrogen Council. And I think today hydrogen is really seen as part of the solutions in order to decarbonize our economies and also to achieve the carbon neutrality by 2050. And I was just mentioning one part of the solutions, an S, also acknowledging that hydrogen is not the silver bullet. It's part of the energy portfolio we will have to develop in order to achieve this carbon neutrality. And how can we do that in particular for hydrogen? Is really to need to create trust and also long-term commitments. Trust that the hydrogen we are now producing is really low-emission hydrogen, and also long-term commitments to ensure that when industry is investing, and also industry either produces or uses, it's in a long-term vision, so that we need these long-term investments. And in order to do so, what we have to put in place is really to put in place strong, stable rules, and not to focus on colors. What matters is the carbon footprint, and not the way you have produced your hydrogen. And here you see that another way to create this hydrogen market and hydrogen economy is also to favor the development of an international trade. And as hydrogen, this is the beauty of hydrogen. Everyone, any country can produce hydrogen. And any country can use hydrogen in many different applications. But of course, some countries may be able to produce much more than they have to consume, while others will have to import hydrogen because they cannot produce the amount of hydrogen they have to consume to achieve this carbon neutrality. And that's why we really need to support the development of an international trade. And also by doing that, and here you can see this is one of the outcomes of the second last International Hydrogen Trade Forum ministerial this May in Rotterdam, they just shown that by 2050, if we favor the development of this hydrogen international trade, we could save $4 billion just owing to these international exchanges. So this then will just really support the development of a whole hydrogen economy. And so now we have to really answer that question. How can we reduce uncertainties in order to favor investments and developments? How can we create this trust, and how can we answer the question that it is clean hydrogen or low emission hydrogen I am producing, I am buying, I am financing, or I am using? And here we see the critical role of certification. And really certificates are here and have to be developed in order to ensure that the product you are selling, you are using, is really compliant with the regulation put in place in your jurisdiction. And by developing these hydrogen certificates, This will also really allow the users about the choice they want to make, and also to ensure transparency about all the attributes, all the values of the hydrogen they are using. And this can also then, of course, also really demonstrate the full compliance with the regulations. So you may use that hydrogen following your local jurisdiction. And by doing so, then you will be able to create a market, and an international market. So certification really supports to increase the customer trust, also to create demand pool, and to facilitate and to favor cross-border trade. And just regarding certification, there are two main types of certificates. Usually, or in many other, like for electricity, what is the most used is reporting and disclosure as a voluntary certificate, and using in particular the exchange of custody of book and claim. But this is for the customer information. But regarding regulation, you have to be mandatory certificates in order to ensure this regulatory compliance. And now more and more certification schemes are developed in order to meet this regulatory compliance. And there are many countries already developing such kind of certification schemes. Here you just have some examples, and that's great. Everyone is working on that critical topic. But on one hand, it can also be seen as a problem. In particular, if there is no coordination, because instead of facilitating international trade, it may just create some additional burdens. Why? Because if these certification designs, requirements are not compatible, there might be then a lack of fungibility of these certificates, and this may just make things much more difficult instead of facilitating. So that's why we really need to work on this mutual recognition of certification schemes in order really to facilitate the development of international exchanges. So it's easy to say, but how can we do that? Or try to do that as soon as possible? That's why during the last COP28, almost 1 year ago in Dubai, we have signed this declaration of intent, signed by 39 countries, in order to just agree that this is a critical topic countries have to collaborate to make it happen. And now, how to implement? First, you see the overarching approach is first, if we want to understand each other, we need to speak the same language. And that's why we have developed, within the Breakthrough Agenda, and also with the H2TCP and other organizations, a so-called certification hydrogen 101 paper. And 101 paper means it's maybe more or less your dictionary where we can agree, and as you can see here, what is a certification, what is a certificate, what do we mean by certification system, certification scheme, what are the main actors, what are the link between these different actors, and the terminology used. So this is one first step, is really to say, okay, let's agree on definitions and let's use the same terminology so that we can understand each other when we will go much more into details. And this 101 paper, version 2, has been released 3 weeks ago at the SAM-MI G20 meeting in Brazil, and you can freely download it on the IPHE website, but also on the IEA H2TCP website, you have the link. So once we could agree on common language, the next step is also to agree on common technical recommendations. And these recommendations may be based on harmonized underlying methodologies. So this is exactly what we are doing, for instance, as an example, with this methodology to quantify the greenhouse gas emissions. And we just had a 2.5-day meeting here in Seoul to work on this ISO international standard, to agree on how we can quantify the carbon footprint of your hydrogen, regardless the way you have produced it. But we need to agree how to do. But it's not only dealing with this attribute, it's also regarding conformity assessment, auditing, because it's one thing to provide data, and even if you're using same standards or same methodologies to provide this data, someone has to check that what you've done, it has been done in the right way, and we need also to check that the people verifying what you've done are doing that also in the proper manner. And there are already existing also standards, in particular from the ISO, dealing with that. So this should then really increase the trust and the transparency of what has been done, how it has been done, and how it has been certified. And To do so, at the IPHE level, for instance, we have a specific certification mechanism task force where we reviewed more than 20 certification schemes. And as you can see here, there are key elements on one certification scheme. These 4 elements: product attributes, and carbon footprint is one of them, but not only. You have also some other environmental, like land use or water use, or even some social attributes that you may allocate. And then you have also this operation setup and procedures, how you are doing. And the chain of custody. Are you using book and claim, where there are no physical relation between your product and your certificate? Or are you preferring using mass balancing, where there are some reasonable physical links between your certificate and your product? And what are the words behind? And finally, if we want to have an international trade, you also have to ensure that if you are exchanging data and exchanging your certificates, it is trackable and traceable. And so we need also to have a very strong and robust information technology. And when we are checking all these different certification schemes developed or under development, we just see that there are many discrepancies. And sometimes people are using the same word with totally different meanings. So this shows that we really need to harmonize and to work all together on that topic. And now, as mentioned, the idea is to work together, and how, and this is exactly what we've been asked at COP28, IPHE and H2TCP, to try to coordinate these activities under the umbrella of the Hydrogen Breakthrough agenda, and to try to find these common approaches. And the idea at the end is really to move from this, for your left-hand side graph, where you see exporting countries, importing countries on the right, but of course exporting countries may have to have some certificates in order that the hydrogen they are producing is compliant with local regulation, and for instance, in order to receive some incentives. But then they may have to proceed to a second certification, depending on the country where they want to export. So they may sometimes have to provide 1, 2, or 3 different certificates for different countries. And this is very tedious and can also lead to high costly activities. And the idea is to move on the right-hand side graph, where we may use a common international database, where we could agree on how, if it is recognized, or some attributes are recognized in one country, they are mutually recognized in other countries. And what we've seen also as preliminary takeaways in order to go there is the solutions we may provide have to be politically feasible, but also pragmatic on the technical level in order to be implementable. The second point is also achieving mutual recognition has to be seen as an incremental process. We cannot be at the end in one step. And first, we need to ensure that there is a common understanding of the purposes, the objectives, and the requirements of these certificates. And then we develop these common tools to allow comparability and compatibility. If it's not exactly the same, at least that you can compare in a fair way, in a transparent way. And then we can also try to converge on thresholds and on commonalities. And to address this very complex topic, we only see a modular approach. And this, with time, of course, and the more people we are and the more resources we put in that, could happen quite fast, at least some first demonstration. And as mentioned before, we really also need to develop a functional, secure, and reliable digital framework. And in order really to allow this interoperability and transparency, which is really key if we want to create trust. So in conclusions, I think that we all agree today that hydrogen is a critical enabler of the energy transition, that international trade will reduce the infrastructure investment needed for the emergence of a hydrogen economy while facilitating that in these international exchanges. And to do so, we really need robust, stable, and transparent regulations, codes, and standards. And certification here is really seen as the cornerstone of all these activities. And IPHE, as a government-to-government partnership, is really pleased to contribute to this international effort and to act, I would say, as a coordinator in order to ensure that we not only facilitate international collaboration, but we ensure coordination to avoid duplication as much as possible. And as mentioned, it's not only a matter of regulators, it's also a matter with private parties, and that's why it's also very important that we have strong public-partner partnership put in place in order to ensure that both parties are working in a harmonized way, with the objective to make our planet great again. So thank you very much for your attention.
Thank you very much. Thank you very much for sharing your insights on the importance of standard certification for building a clean hydrogen ecosystem and the role of international standards in preparation for hydrogen trade. 네, 청정수소 생태계 구축을 위한 표준 인증의 중요성과 또 수소 교역에 대비한 국제 표준의 역할에 대한 발표를 전달해 주셨습니다. 네, 이렇게 첫 번째 발표에 이어서 또 많은 순서가 준비되어 있는데요. 현재 앞쪽에도 좌석이 마련이 되어 있습니다. 참석자분들께서는 앞쪽으로 이동하셔서 조금 더 가까이서 본 포럼 함께 해주시면 고맙겠습니다. Following the first presentation, we have many more talks and panel discussions lined up. And there are also seats available up front, so we kindly invite attendees to move forward to fully engage in the forum today. Thank you very much. 바로 이어서 OECD 이문경 정책분석관님께서 발표를 진행해 주시겠습니다. 여러분 큰 박수로 모셔보도록 하겠습니다.
Hello, 안녕하세요. Thank you so much for inviting me to this very interesting event. I'm very glad to represent OECD and present some of the work that we're doing in Clean Hydrogen Fora, collaborating with our member countries. Just briefly about OECD, for those who are not familiar with what we do and who we are an international organization with 38 members. And then we are working as a policy advisor and also providing the policy platform for our member countries and beyond for our partners to work on building the consensus on the standard and as well as process initiatives. Thereby, we help drive and anchor reform more than 100 countries at the moment. Before we go further, I would like to a bit of sharing the key messages and basically based on the work we have been doing since 2022. So at the OECD, we are looking into various matters around the climate change, and particularly under the team that I work for, which is CEFIM, Clean Energy Finance and Investment Mobilization Team. We work closely with emerging and developing countries to support them identifying enabling solution and financial solution for accelerating the clean energy transition as well as industry decarbonization. So since 2022, under the industry decarbonization financing workstream, we have been looking into clean hydrogen issues. Particularly, we are contributing to the various international initiatives, as you heard many times throughout this conference. Breakthrough Agenda, we are a member knowledge partner, as well as H2 Global in Germany, and we are currently working very closely with World Bank colleagues, putting forward the 10 gigawatt initiative. So my presentation consists of giving you a bit of overview of what we have been learned throughout the work that we have been doing. And then I will share some of the insights that we have gained, which is upcoming report that we have worked on with World Bank colleagues. So before we going further, I would like to highlight what is the issue that we want to address from the OECD side. What we're observing at the moment, there's a lot of hype in the market around clean hydrogen, but there has been a significant slowdown in terms of achieving the FID, final investment decision. And so far as the projects through 2030, the current total investment pipeline has been around $319 billion, but only $29 billion have been achieved FID or near FID. That being said, while more than 40% of project pipeline is located in emerging and developing countries, we're only seeing, for instance, 6 projects has achieved FID that is above 10 megawatt size. If we lens in a little bit of FID achieved or near FID projects, we are observing 4 different types of business model. The first starting with the decarbonizing existing process, which is an effective way of creating a large amount of hydrogen demand and supply with a relatively small investment, notably by using existing assets and facilities. This is a great incentive for the companies in oil industry or gas and fossil or ammonia production industry to avoid the carbon lock-in or stranded asset issues. For instance, doing the case studies that we have been doing since 2022, which I will share more in details in the later slide, we notice the companies such as Ecopetrol of Colombia, ExxonMobil, Shell, Sinopec, those companies are leading developers and project initiators under this model. And second component is what we call the export model. So this is somewhat overlap with the first model, but we see it as whole business structuring for the clean hydrogen projects is aiming to export to the partner countries. The common observation that we're seeing in the market is developing countries are exporting the hydrogen or hydrogen derivatives to the advanced economy, for instance, from Egypt to the European Union countries. In this case, this is effective mechanism particularly to address the one-sided offtake risk. So this is also something that we observe as a main business model. Third is utility goes downstream, meaning that the OEM companies or renewable project developers are investing or planning to operate electrolyzer plants as a complementary or diversification strategy of their business. So they are the also main leader. Here we see emergence of new ventures or new companies leading the business development of clean hydrogen projects. For instance, recently we saw some companies in Mauritania or Namibia who are the new companies that are driving the clean hydrogen project development. Last but not least is the hydrogen hub or hydrogen innovation valleys in some jurisdiction. This is emerging area we are seeing here and there in emerging and developing countries. However, unfortunately, we are not seeing that much FID under this model. But so far, according to Mission Innovative, Hydrogen Valley platforms are counted as 98 hydrogen valleys in the different part of the world in 33 countries, with a total investment volume of 173 billions, but still FID is not seen under this model. So now we have seen a bit of outlook in terms of how the landscape looks like in terms of clean hydrogen from the OECD and together with World Bank colleagues before we launched the 10 gigawatt initiative. What we have done is to understand why the clean hydrogen projects are not achieving the FID as we want. And one of the key issues we pay attention to is high cost of financing. Last year work, we highlighted that the range of cost of financing for clean hydrogen projects could be around 6 to 24%. Of course, this is a very wide range of number, but still our intention is to understand where we stand. Then if the high cost of financing is high, what are the factors that driving this cost of financing issues? So we did a survey with World Bank with 40 developers who have experience in this field. And as you can see from this chart, 4 priorities are linked very much to the offtake, and there's one on the political risk, but this is due to the nature that a lot of projects are based in emerging and developing countries. Building on this, this year we're launching De-risk Instrument Initiative, which is toolkit to power the emerging and developing countries to tackle the issues that we are seeing in terms of cost of financing. I want to highlight that, of course, we are aware that enabling condition is crucial, which is enabling infrastructure as well as policy stability in emerging and developing countries is crucial. But in this context, we just lens in on the project life cycle and project level details to make the early mover projects to work to scale up the projects and accelerate the learning curve. So as you can see, the risks are varied. Before what you have seen in the previous slide is more linked to the pre-FID risk, which is offtake infrastructure license, infrastructure and license to operate risk is more linked to the pre-FID. Of course, after the even FID, there are certain risks that is still present, such as the EPC overrun, offtake default. Also, the technology non-performance and withdrawal of the regulatory incentive is coming as a key risk that has been identified in the different project cycle. So to develop the toolkit, what we have done is compare the asset with different asset that has a somewhat similarity with clean hydrogen. Of course, based on the project cycle and location and ticket size, this chart may not accurate. The risk could be varied, depends on which project we're talking about. So bear in mind this is average projects and average risk that we're seeing in most of the projects. So what we have done is did the basic comparison based on the risk factors that investors often assess when they are deciding the investment. So commonality that we found with offshore wind and the clean hydrogen projects are both exposed to significant financial risk related to intermittency of the production and market price fluctuation, which is basically merchant risk. But for offshore wind, this is driven by the often high volatility of a power market and cartel risk, whereas for clean hydrogen, it is mainly due to the lack of transparency of the clean hydrogen price in the market. Also, what we have seen in terms of similarity with LNG, because it's often compared that clean hydrogen has somewhat similarity with LNG projects at the early stage. It is true that both assets have a complex project structure, but the risk that present for clean hydrogen could be different, depends on whether project is vertically integrated, whether co-located projects, or it's standalone projects. So still somewhat similarity, but there's still a lot of understanding has to be done to assess the risk profile of the clean hydrogen projects. So building on this, we selected 6 de-risk instruments that has been deployed throughout the projects of the LNG or offshore wind and renewables, etc. And then based on that, we set out 3 criteria to understand the effectiveness of those de-risk instruments. And based on that, we have conducted the 2 rounds of expert interview and the survey, and concluded that we have identified few high priority de-risk instrument that government or the market could focusing on. The chart shows that if it's a darker green, it's a high priority, and the lighter color indicates it's a less priority. What results shows, of course, the preferred de-risk instruments is closely linked to the offtake guarantee, such as contract for differences, as well as any devices that is linked to offtake risk is preferred option. And surprisingly, there was a political risk investment. I use the surprising because often for the countries who are advanced in the hydrogen discussion, the political risk is not a key factor. But just reminding you, there are a lot of projects that are intending to take place is in emerging and developing countries. So for investors, particularly European investors, are focusing a lot on de-risk some of the political risk or macroeconomic risk they are seeing in this market. One of the key interesting factors we found in this survey is actually technology risk. We often hear from the investors that they perceive the technology risk is very high, but when we conducted an interview and those who already done some transaction in the hydrogen, they mentioned as long as the offtake risk is addressed, they think technology risk can be easily handled through EPC contract or other way around. But of course, there is a financial de-risk instrument, but we also, from the OECD side, we acknowledge the importance of international coordination and cooperation. You heard a lot of these words today throughout the clean hydrogen discussion, but from OECD side, what we have done is looking into what's happening in this fora. So as of May 2024, there are more than 50 national and regional strategies that is established by different parts of the world. And we have identified 46 international initiatives around the clean hydrogen. And we excluded actually bilateral collaboration here. So there are a lot of hype, but also interest and enthusiasm going on to make this work. But still, there's a lot of work to be done to reinforce what we are doing as international, in terms of international coordination. First on, we noticed there is a gap around the coordination of finance flow, meaning that a lot of IFI has some standalone program, but they are not cooperating in terms of make the project more affordable for the investors or make it commercially viable. So we recommend very much to use the platform to channel the IFI or DFI's money into into the one area to make the early moving projects to work. Of course, as highlighted by many colleagues here today, the feasibility study or understanding of the project structure is crucial. So one of the key areas we think is important is knowledge sharing, but also harmonizing the appraisal and procurement process, particularly for large-scale projects. I'm almost there, but interesting fact that we want to highlight is so far OECD have working on looking into real case, real projects. This is mainly demand-driven, meaning that a lot of our member countries wanted to understand what could they do more or they should do to make their, the projects in their country work. So we try to identify success factor through looking into case study of the clean hydrogen in different parts of the world. So far, we have developed 21 case studies and 11 case studies around de-risk instruments and financial instruments, and also the policy measures that are taking place globally. These are all available on our website, free of charge. This case study highlights basically enabling condition has to be there before you talk about de-risk instrument for sure. And once it's there, concessional financing is a very much important factor to consider and mobilize to make the project viable. And what we are discussing when we talk about concessional loans is to be aware that we're not crowding out the private investor here, of course. That's all from my end. Thank you very much for your attention, and please reach out if you have any questions and you want to know more about our work from the OECD in clean hydrogen. Thank you.
Thank you very much. 네, 고맙습니다. 금융 관점에서 본 청정수소 생태계 확대에 대한 위험 요소들과 또 리스크 저감 사례에 대한 연구에 대한 발표를 잘 진행해 주셨습니다. 다음은 프라운호퍼에서 오셨죠. 크리스티안 도이치님께서 발표를 준비해 주셨다고 합니다. Next, I'd like to invite Mr. Christian Deutsche from Fraunhofer to deliver his presentation. 네, 여러분 큰 박수로 맞이해 주시기 바랍니다.
So, thanks a lot for being invited here, and I'm very happy to have the chance really to present you some latest results. Only a few words regarding my person. My name is Christian Dötsch. I'm head of the Fraunhofer Institute Umsicht in Germany, and I'm the spokesman of the Fraunhofer Energy Alliance. This is the alliance of the 20 institutes. They are related to energy topics. This is our home institute here. This is Umsicht. You can see the key factors or key numbers of our institute there on the slide. Very important, we are the largest institute for process engineering and the 7th largest institute at all from the Fraunhofer Society nowadays. There we have 4 main focus topic areas. I only want to focus on one of these research topics. This is the green hydrogen. And you can see what are the main points of interest for us there. We have the material and component development, we have the stack and system optimization, and we have the testing and deploying. And what is also important, keep in mind, if you're not so familiar with Fraunhofer, Fraunhofer has the mission to gap the bridge between the university research and the industrial research. That means all the things we are doing there, we want to do to bring some technology from the level from 0.3 up to 7, 8, 9 to go to the industry. Always keeping in mind, the industry wants to have a solution. This is near to the scale they can use, they can operate itself. In the next 2 slides, I try to give only a very, very brief overview about main topics, what we are doing there. On the one hand side, we are really dealing with catalyst development. Development means we develop new catalysts, and we are doing also the scale up of the production of this catalyst. One of the main points there is the design and synthesis of noble metal-free catalysts for the hydrogen evolution reaction. That's the main point there. but also the application on membranes and so on is important. You know this from the fuel cell technology. Then another point, I want to focus more on this today, is the bipolar plates and the electrode development. You can see an electrode there, which I will introduce on the next slides. And the last one is to develop stack concepts for the conversion, because this new type of bipolar plates allows for more flexible solutions, more efficient solutions. And then coming back to the point, we want to bridge the gap between the small scale and the industrial scale. That means the university scale. And on the left-hand side, you can see more or less the lab scale of university and also of our lab. That means we are producing very small material sheets, the size of a post stamp or something like this. And then we want to go to really application, to a real size. You can see on the right-hand side nowadays we are working with sheets of different materials like membranes coated with catalysts, for example, or bipolar plates in an area of a sheet of paper, of a double sheet of paper, something like this. And the next step will be the 1 square meter stack system. To make this more concrete for you, what are the topics, what we can do, I want to show this with 3 different projects we have with industrial partners. And there you can see the different technologies we are developing at the moment. The first project regards to low temperature fuel cells. The second one is to the low temperature electrolyzers. And the third one is the co-electrolyzers for methanol production. So let's start with the low temperature PEM fuel cell and the novel compound bipolar foil there. It's a public funded project with different partners. You can see the partners on the last slide. This is a picture of our bipolar plates. That means we have, as most of these bipolar plates, 2 half cells. They are welded together. And where is our aim really to make a new development of the stack design because of the new options of this new bipolar plates. And probably it makes sense really to introduce to you this technology because this is unique. No one else is producing bipolar plates in this way with these characteristics at the moment. So it could be really a game changer. We start with really thermoplastic polymers. There we have some cryogenic grinding for this. Then we go to drying, mixing, and putting in fillers. They are graphite and so on, carbon black. And then we go to a multi-roll rolling process, and we can produce directly from the powder the end product. And you can see we can do it on a rolls because it's flexible. It's a thermoplastic material. And nowadays we make the next step embossing it because we need a flow field inside. You can emboss it like every thermoplastic material. In the future, we want to make a roll embossing process, but at the moment, it's really a batch process for the embossing. And the next step, you can see in the right-hand lower corner, is the welding of the bipolar plates together, because you have to know if you have these bipolar plates, they are cooled, they have intercooler water inside, and therefore we need 2 half cells, and then we weld them together to get a full bipolar plate. Last but not least, some surface optimization by lasers, and then laser welding it in a thermoplastic frame. And this is the main point there, because of this thermoplastic framed material, we can laser weld the whole stack system to one big block. And there you can see the main component on the right-hand side. This is the bipolar plate. I tried to bring it with me with the hand luggage in the aircraft to show you this is the style we can produce today. This is a real stack size or cell size at the moment. With this size, we want to go to different users. They want to use it for the trucks to build in a fuel cell there for moving electric trucks at the end. And very important, you can see this is not only our development. We have made this core material, but we have partners there. They are mentioned here on this last slide. And there you can see these different partners bring in their own expertise, and that's very important in all the projects, that we try to make the best team, because we are not thinking that we are the best in everything. We have really good researchers at Fraunhofer, but we always need partners from industry or from other researchers. And you can see this is the first big project. At the moment, we would say it's really close to the market. At the moment, we're developing this with different partners. Then was the next step to say, okay, now we have a fuel cell made of this material, let's go to electrolyzers. Because you know, electrolyzers have a high cost problem because it's all this titanium bipolar plates. This is really cost intensive. More or less all the PEM electrolyzers have titanium bipolar plates, and there we try to go with our material and saying, okay, we can do this, it's working still in the fuel cell technology. Let's have a look, it's working in electrolysis. And I know you are mostly experts on this field and know electrolysis is a very high corrosive environment. So, and if you go to the anode, it's horrible corrosive. And so we tried to make it better. And we started there using our traditional material with minor improvements, I would say. And we tried to put this in this stack system. We optimized the PTL, the porous transport layers. They are made up to date also from titanium. And we tried to do the same like for the fuel cells, to weld each part to the next one. Because then it's a main advantage, there are no seals in between. And without seals, it's getting much easier to tighten the whole system at the end. And then there was the really unexpected result. We saw that our, I would say, normal bipolar foil is working in the same way like in the fuel cell without degradation. We did this over 600, 700 hours, and we have no chance to see more degradation than a normal titanium bipolar plate. So at the same stability, there's no corrosion to see, and so we are very, very optimistic to say, yes, it could be a solution of the future. And the main point is, we see today it is cost competitive to each titanium solution, and we are optimistic if we are doing this in a more efficient production way, it's getting much cheaper, because the material costs are really on factor 10 to 100 cheaper than this of titanium. And we make a publication in the peer-reviewed journal, and we were very happy because on the one hand side, it was a great success, this peer-reviewed journal. On the other hand side, you can see also there was from Nature Energy a highlight mentioned regarding our new product there in the article regarding this. And so we are really proud that we have this new material and this new material for electrolyzers for research established at the moment. Let's come to the third and last example. We want to go to the co-electrolysis there. There's a project, Pathway to Green Methanol by Low Temperature Co-Electrolysis. To say it clear, I can say it on the next slide, our part from Fraunhofer is the co-electrolyzers, not the methanol production. We do also research on this, but in this project, our part is really co-electrolyzers and not the methanol production. This is a very interesting project because it's located in Leuna. You're not familiar with Germany, I assume. Leuna was the city where it was first introduced, this pathway for methanol, but with fossil fuels. And nowadays, 100 years later, we introduced a new one, the green methanol, because we are thinking about aviation fuels and other applications. So this project started last year. We are at the moment building this co-electrolyzers there, and another partner from Fraunhofer is testing the whole system at the test site, and a smaller startup company is producing the methanol production unit. Here you can see our co-electrolyzer stack at the moment. This is the scale of a 5-cell stack. For the next step, this is erected at our institute. Now we make the 55-cell stack. This is under construction, and this will go to Leuna next year. And you can also see here the key figures of this deck. Main point, which is important, is the pressure. We will operate with roughly 100 bar. That's very important for this, because if we can produce this syngas coming from water and CO2 from, I don't know, from exhaust gas from a steel mill or from some other sources, we can produce the syngas, the mixture of CO and hydrogen, on 100 bar, because the methanol process needs this pressure. If you use some other co-electrolyzer with a lower pressure, you have to compress the syngas, and then the efficiency of the whole process will go down. Therefore, it was so important to produce this, and you can see the size is roughly 450 square centimeters at the moment. So this was really Fraunhofer in a nutshell. If you are interested in this technology, or in total to cooperate with Fraunhofer in Germany, with the Energy Alliance, or do you have some special questions regarding the bipolar foil here I've shown to you, don't hesitate to ask me after this presentation, in the break, or to my colleague sitting in the first row, Joe Kim there, is our representative here in Korea, and so he's not 24/7, but I would say most of the day available. You can contact him, and he would be very keen really to make the contact to me, to us, or the best partner from Fraunhofer, because Fraunhofer is a society of 32,000 members working for Fraunhofer, and I think we have always the right expert for your problem. That's it. Thank you for your time, and I hope it was interesting for you. Thank you.
Thank you very much for your presentation, focusing on the current development status of renewable hydrogen production technology being conducted at Fraunhofer. 네, 프라운호퍼에서 진행 중인 재생수소 생산기술 개발 현황에 대한 발표 잘 들어봤습니다. 다음으로는 에머슨 마틴 반데르 메르의 아테 총괄국장님의 차례인데요. 총괄국장님께서는 사정상 이 자리에는 함께 하시지는 못하셨지만 또 영상으로 발표를 준비해 주셨다고 합니다. 바로 화면을 통해 만나보시죠.
Yeah, my name is Martin van der Merwe, and I am the Director for Sustainability and Decarbonization in Asia Pacific with Emerson. In today's presentation, I'll share with you how Emerson's technology impacts hydrogen project success and share some proven results from projects that we've been involved with. Emerson is a global automation and software leader, delivering solutions globally for over 130 years. Through our software control and intelligent device business groups, we've provided the broadest automation portfolio across all industrial and manufacturing segments in that time, including the evolving decarbonization segments such as hydrogen. A few years ago, Emerson acquired a controlling stake in AspenTech Technologies, and together we continue to innovate and develop software and control solutions to support the hydrogen industry. And I will present some of those synergy solutions today. So what does Emerson's portfolio consist of specifically, and how does it apply to the hydrogen value chain? Well, as mentioned, Emerson has one of the broadest automation portfolios in the industry, starting from the foundational layer with our smart instrumentation to measure process variables and valves to control those processes. The hydrogen industry specifically requires accurate, traceable, and safe instruments for hydrogen production, storage, and transportation applications. This forms part of what we call the intelligent field. The instrumentation provides data into our control and safety systems, and with applications for advanced control, asset management, SIL3 capable safety systems, and edge devices, this control layer serves data securely into the enterprise layer, where our powerful analytics, software and process optimization, predictive maintenance, energy management systems all reside. As the hydrogen sector continues to evolve, we continue to innovate our solutions to solve the challenges of this growing industry. Some examples of that include the development of our high pressure and liquid hydrogen Coriolis flow meters, liquid hydrogen isolation valves, including the pressure release devices, for which we recently received the Preliminary Innovation Award at the H2 Meet conference. Of course, one of the key challenges for hydrogen projects is driving down project costs. And while automation typically only presents 2 to 3% of CapEx investment, taking advantage of the capabilities that automation provides can save a project in excess of 30% in construction and engineering CapEx investment. This is achieved primarily through savings in infrastructure costs and reduced engineering effort and risk. The intelligent field with wireless instrumentation and streamlined connectivity reduces the need for a significant amount of structural engineering, cabling, and testing. Containerized software and control applications at the edge reduces the equipment required, such as server and control panels, which minimizes the required footprint, power, HVAC, and so on, while securely serving up data into the enterprise cloud, where these contextualized data sources can be easily accessed by the correct business department for engineering, maintenance, safety, and business management. So this is what we call boundless automation. So it becomes a bit more critical then than ever to engage and evaluate your automation technology partner very early. This traditionally only occurred after FEED, but that limits the ability to maximize project cost savings that I mentioned before. So we see projects that consider the automation impact at feasibility stage or even at pre-feasibility being able to take advantage of these opportunity savings. In order to improve the viability of the hydrogen sector, scalability and size will be critical. Many green hydrogen projects start small as 1 to 5 megawatt pilot projects, often using non-industrial simulation applications and PLCs. These projects typically aim to demonstrate and evaluate the performance of the hydrogen application. From there, we see the first phases of projects in the range of tens of megawatts, implementing modularized industrial automation technology. Many of these projects have future phases to scale into the hundreds of megawatts. And as these project sizes increase, so too does the complexity in the requirements on safety design, the efficiency, maintainability of the equipment, and even remote and autonomous operations. We see on these scale projects that PLCs typically on electrolyzer skids are no longer fit for purpose. They become a bottleneck for effective data flow and efficient operations and management. And so the importance of front-end digital twins and the deployment of fit-for-purpose automation with easy access to data from the field devices play a much more important role to minimize the CapEx of these projects. So that is the concept, but let me give you a real-world example to explain how that works. A customer has developed an integrated green hydrogen production and storage plant concept. They engaged Emerson early and learned about AspenTech's Fidelis solution that allowed them to run Monte Carlo simulations of their energy sources, electrolyzer efficiencies and stack configurations, storage capacities, and offtake schedules. They ran multiple what-if lifecycle scenarios in Fidelis to validate the feasibility of their project. And using this software, they then further developed detailed process models using Aspen Plus and concurrently used the HYSYS models from their selected electrolyzer supplier to create a high-fidelity hybrid process digital twin, together with AspenTech's AI-optimized 3D OptiPlant design. Using the process data, they specified equipment and optimized the CapEx cost using AspenTech's capital cost estimator tool. Because they engaged us early, they were able to identify with this capital cost estimator tool that the architectural benefits of Emerson's electronic marshalling with distributed charm I/O and wireless instrumentation not only simplified the design, but saved them in the order of 30% in construction costs. As front-end engineering and design commenced on this project, they used the same hybrid process digital twin and interfaced it with Emerson's MIMIC simulation software. This software simulated field values from the process model and presented it to Emerson's cloud-based DCS simulated automation digital twin, where all the control strategies, the HMI, the alarming, ramping sequences for the electrolyzers and energy management of the hydrogen plant was simulated and optimized. Emerson's technology is focused on the fit-for-purpose nature of hydrogen projects, as I said before, and we eagerly participate in many of those smaller scale innovation projects. I've summarized a few international projects like Neptune's Poseidon project that uses offshore platforms in the North Sea, converting them to green hydrogen production stations that blend hydrogen into the existing gas infrastructure. We also support new electrolyzer and fuel cell technology developers such as Cavendish's AEM and capillary technologies, and we also have significant engagement in many hydrogen mobility solutions with H2Hauler and Biotech, SoCalGas, and here in Korea with Cohygen and most recently HiIS. But our technology also plays a critical role in the integrated systems required for hydrogen production. We've been involved in hydrogen production projects for a long time, since the Air Liquide site in Canada was commissioned, and we have gained significant experience in our engineering and support teams as we continue to implement projects across the many regions that we serve. There's not enough time to go through all of these references, but I'll dive into a bit more detail on the Mitsubishi Chevron Advanced Clean Energy Storage, or ACES, hub project, just to illustrate the scaled complexity of this 220 megawatt green hydrogen project. The aim of the project is effectively to a combined cycle peaking power plant using clean hydrogen produced from excess renewables and then stored into two massive underground salt caverns capable of storing more than 300 gigawatt hours of hydrogen energy. When the electricity demand is high and the pricing is favorable, the hydrogen is used to run an 840 megawatt hydrogen capable Mitsubishi turbine using hydrogen from the stored salt caverns. This project selected Emerson's technology for the entire automation scope, from DCS, the safety system, the PLCs, asset management systems, field instrumentation, and valves. To highlight the complexity found in this project, which is one of the largest green hydrogen production projects under construction currently, I'll run you through the architecture and design concept. The project uses 45.5 megawatt Hydrogen Pro electrolyzers that are configured into 20 trains of 11 megawatts each. Having this many electrolyzers and variable energy supply presents quite an interesting and complex control challenge. We firstly need to consider the state-based operation of each electrolyzer that's represented and illustrated here in the top left. In our automation platform, we have simplified the configuration complexity of such state-based systems into function blocks that are easy to understand, configure, and fault find. Secondly, we needed to develop algorithms to prioritize and optimize the electrolyzer train starting sequences based on the power demand set point from the energy management system. Now, you don't want to develop and test this for the first time on the physical equipment. So the project used extensive modeling processes and automation digital twin deployments, as I shared earlier, to develop these test algorithms and implement them in the virtual space in these digital twins prior to implementing them on the equipment, which is currently being commissioned. So I hope that gives you a bit of a flavor of the complexity of larger scale projects that Emerson is involved in. So to summarize, ensure that you engage, identify, and leverage your automation technology partner early in the development of your hydrogen project so that you can take advantage of boundless automation with process and automation digital twins that will deliver market advantage through investment certainty, lower capex cost, lower operational costs, operations optimized to reduce OpEx over the planned life cycle of the facility. So if you found this interesting and you'd like to connect with our team, please visit our booth and also be sure to join our Chief Sustainability Officer, Mike Train, during the panel discussions later in the week. Thank you very much.
Thank you very much for the wonderful video clip. 네, 고맙습니다. 이렇게 해서 총 4분의 발표를 들어보았는데요. 지금부터는 좀 더 심도 있는 대화를 위해서 패널 토론 시간을 갖도록 하겠습니다. 이번 패널 토론은 세종대학교 정훈택 교수님을 좌장으로 모시고 진행이 될 예정입니다. 그럼 먼저 좌장님을 무대 위로 모셔보도록 하겠습니다. 여러분 큰 박수로 좌장님을 맞이해 주시기 바랍니다. 네, 고맙습니다. 바로 이어서 또 패널 분들을 무대 위로 모셔보도록 할 텐데요. Next, I would like to invite our panelists up to the stage. First, please allow me to invite Executive Director Laurent Antony of IPHE. Please welcome him with a big round of applause. Thank you very much. And I would also like to invite Ms. Lee Moon-kyung, Policy Analyst at OECD. And Director Christian Doichi of Fraunhofer. Thank you very much. And last but not least, I would like to have Mr. Son Hyuk-chun from Emerson as well. 네, 고맙습니다. 이제 그럼 좌장님께 마이크를 넘기도록 하겠습니다.
Yeah. Thank you to all the presenters for your very informative talks. And I also thank you to the Korea Hydrogen Alliance in organizing this very nice forum. This forum covers key aspects necessary to develop hydrogen industry from technical and non-technical perspectives. I'm sure this forum is very helpful in advancing hydrogen technology. Hydrogen, as you know, is essential in mitigating global warming. In particular, hydrogen can reduce carbon dioxide emission from very hard to decarbonized sectors such as industry, aviation, maritime, and heavy-duty transport. So I think hydrogen industry is crucial for net zero. So this is why we put all our effort in this hydrogen industry, okay, including this forum. Okay, so let's move to the discussion session. Laurent, let's start with you. So you talk about the certification. It sounds very complicated, right? And it sounds you just started this task. So would you share your kind of plans for this task and a kind of timeline, a final goal? So when we can get this certification?
Yeah, thank you. Thank you for your question. as you mentioned, and as presented previously, certification systems can be quite complex.
Yeah.
And I would say, of course, certification is not new. It has been developed for many different either products, can be energy, like electricity, you have certificates of electricity. But the hydrogen here, what is complex is to ensure mutual recognition. In order to ensure, as you are mentioning, we need to create this industry and we have to increase the clean hydrogen demand.
Yeah.
And to do so, we really need to create trust. And this means to have really stable, robust certificates. And as hydrogen will be exchanged over the world and quite fast, at least even maybe start this decade,
Yeah.
we need also to agree on, if we say, I am selling low emission hydrogen, the buyer is telling, yes, I trust you. I believe it's a certificate. And that's why it's very complex. But we need to start. And the idea is really to start first to assess what has been done.
Yeah.
And then to agree, as we're mentioning, regarding this terminology. Now we have in place this certification 101 paper. So now we just would ask people to read, to use it, to provide some comments. Of course, we may improve that document, and we'd be very happy to improve it as a living document, I would say. And then to see internationally how we can really work together. And this is really key. And regarding timeline, we are using different existing initiatives. The idea is not to create something new. And you have mentioned that at the beginning there are already, and if you look at the latest Breakthrough Agenda report, more than 30 different initiatives, organizations now dealing with hydrogen. And everyone may do the same.
Yeah.
And we may just waste time. So the idea is how can we ensure we are working together and have a work plan. And the work plan should be, first, as mentioned, speaking the same language, assess what is existing, assess also where the demand is, where the production is, and what might be the first international trade routes.
Yeah.
And there are some initiatives existing, and take these first trade routes, for instance, we may say between Australia and Korea, or between Australia and Japan, or Brunei and Japan, or US and Europe, for instance, to try to see with some first demonstration before the end of this decade.
End of this decade.
Before, I would say.
Okay.
The idea, our plan is to try to develop some first common modules on the certification scheme, and to try with this first, I would say, pilot trade routes to see how we may start to implement that. And so our plan is to give us some more information at next COP to select these first trade routes within the next 2 years when it's put in place, and then to start first implementation of these certification aspects between 28 and 30. And then, of course, learning from these first trials how we may improve. And that's why I was mentioning it has to be politically acceptable, but also technically feasible. And the feedback received by these first trials may they start help to improve the whole process. And then we hope that at least by 2030 we may have some first concrete examples of mutual recognition of certificates.
Yeah, by 2030 you will get a kind of first example, right?
Between 28 and 30 to have some first examples, yes.
Yeah, thank you. Yeah. So then what are the major obstacles in your task, I guess? I think, Would you share your idea?
So the main obstacles is, first, we need to understand each other. And certificates are only here to ensure you are compliant with your regulation. So what we need also to do is to agree on what are the different requirements that we are putting in the different regulations. Of course, regulations have to take into account unique circumstances of a given country. But we need to agree at governmental level what might be some convergence between these different constraints or requirements, not constraints, but I would say requirements that you are putting in your regulation, because the idea at the end is to ensure that we are decarbonizing our economy while supporting the development of a new economy or a new industry like the hydrogen field. And I would say the option you may have in one country may not be the same at another country. So we need to agree, and this is one of the difficulty, also to agree on common aspects, common perspectives,
Yeah.
that then could be also translated into common approaches on certificates. So this really needs to have some international discussions,
Right.
collaboration, coordination, and in order to have this happen.
Then currently, how many countries are involved in this task?
So you see, during last COP29, 39 countries have signed.
39. Okay.
And we have a specific task force at IPHE. The IPHE was 24 members, 23 countries plus the European Commission. But we are open to include, I would say, any country having signed this declaration of intent. So we might be up to 39 countries so far, and we're just, any interested country may sign this declaration of intent, and this is something we are calling and asking also during COP29 and after. Please, if any country is interested in joining this approach, please just come and sign, and we're happy. And as we're also working with other initiatives, and this was mentioned also with you regarding the Hydrogen Breakthrough Agenda. There is a specific priority on certification, regulation, codes, and standards. And here we try to gather as many international entities, organizations, in order to share. So to answer your question, you see almost 40 countries.
40 countries,
And we
okay.
have also different organizations, IPHE, IUHDTCP, UNIDO, UNECE, Hydrogen Council, and other organizations
Okay.
discussing together in order to exchange and to see how we can develop that as fast as possible.
Okay. It looks like you need a lot of fundings. How you get your funding for your job?
This is a good question, and I would say this is exactly something we are today asking to the different countries.
Okay.
If you want to develop really strong, robust regulation, but also standardization, as you mentioned, you need to put in place resources.
Yeah.
And now we are just asking all the different countries, what is your vision, what is your perspective, how many resources you can put in place, or you should put in place in the next years in order to make it happen. And then we will see exactly if it is enough or if we should try to find some additional resources. And at this, I would say, international approach, it's more or less some, I would say, in-kind contribution as each organization or governments are coming in different events with their own fund.
Okay. Is there anything Korea can contribute?
Yes, of course.
Yeah.
I would say yes, of course. I would say Korea is, I would say, is a big player in the hydrogen community, and Korea is part of IPHE working group, IPHE member, and we can just ask if any interested party, in particular agencies, but to just discuss with KTC, also developing the certification approach for materials. That's also a key element. We are only discussing about certification of goods, of the product of hydrogen, but we also need to ensure, and this is conformity assessment, that how hydrogen has been measured, produced, handled, is also done by certified equipments and certified people, skilled people. And so in Korea, you have an active entity, for instance, but CATS can be also quite important. And so you see, Korea can really bring some added value by participating in these international discussions.
Okay. You happen to be sitting at the same table.
Yes, exactly.
Okay, thank you. Yeah, thank you for your comment. Moon-kyung, you present very nice talk. And so actually funding is very important for every work, as you know, I think. But from your presentation, I think I noticed that most announced global hydrogen projects are pre-FID, final investment decision, and with only a few reaching the FID. What your thought on moving project from pre-FID to FID?
Thank you, Chair. Thank you, colleagues, for a very insightful discussion so far. I think pushing forward the projects that we are seeing is a tough question. I have answered and prepared this length of answers. That means the challenges that we are seeing in the market is very complex. It's very hard to tell at this point how the projects individually will be evolved going forward as the market grows, meaning at the moment, there are each projects that reached the FID so far has a different characteristic, different success factor. Either it was government who was involved and de-risk entire financial risk, or it was the off-taker that was designed to be at the very early stage by third party with a strategic interest that drives the projects to reaching FID. So it's really differ case by case. But we could tell from the OECD's experience and the work that we have been doing so far is in some extent very early stage projects that we are seeing that making quite attractive positioning for the investor, it seems like they are having quite similar characteristic with early stage of LNG projects. What does it mean is that the equity investor, who are the crucial players for early stage technology like a hydrogen, they come as also the off-taker. For example, that was the case for the NEOM projects. And what gives the benefit from this structure is that the alliance of equity investor and then different players that are involved in the project structuring. And that brings down significant risk that also push forward a little bit closer to FID. Other factor is obviously the participation of the public sector. If you look at the NEOM projects, there has been a lot of participation from sovereign wealth fund who are backing up the projects, and the significant, more than 6%, if I remember correctly, has been backed by sovereign wealth fund. And this brings the public and private partnership to be more stabilized and makes the project reaching to the FID. Of course, there are enabling factors that has to be there in terms of policy measures, has to have a certain level of clarity. And in some cases, of course, incentive plays some critical role to make the project attractive and confident about the project's direction it has. But the other factor we also think seeing it closely linked to the revenue stream of the projects, because at the end of the day, FID is more or less about to make the projects work, and the working means that I will get my money back throughout the life cycle of the projects. So another thing that we're seeing is the EPC contract policy. So some of the very interesting projects in Oman, also of course NEOM, but there's some projects in Australia, and we won the one we saw in Africa, in Egypt particularly. They have designed very interesting EPC contract, because common understanding around EPC contract is to have a rep EPC contract. But for many cases for the clean hydrogen projects that we are seeing that reaching FID, they designed a single EPC contract led by a very reputable technology provider, or has a significant balance sheet that can back up the default cases. Therefore, any investors who are participating in this deal has more confidence in terms of there will be less of risk around the construction or the operating stage risk for the projects. So these little things obviously pushing the projects moving forward or closer to the FID certification, of course, is crucial, but this has been dealt in depth by the colleague here, so I won't go details. But last point I want to make is, of course, the macroeconomic condition is very crucial, because when we see the many interesting projects that are happening in Brazil, for example, they have very ambitious plan, including in Colombia as well. One of the key barriers they are facing in terms of reaching the FID is, despite the country has a strong interest and they have also certification in place, the barrier coming as country risk premium is coming as a barrier, especially if you want to attract the foreign investors to make the project push forward. Particularly also the case the project is large size, so you need significant capital. So domestic investor or the public investment is not enough to make this project to move forward to FID. So stabilizing macroeconomic condition is very important, but of course complex procedure. The one single solution, interesting solution we saw was that they provide a comprehensive kind of package for the investor who are coming to their country to deliver the products and be off-taker. That was the case for Egypt in the case of Vertiglobe. So that kind of measures are here and there seeing the results, but of course, I understand some cases it's beyond this kind of single solution.
Yeah, thank you very much for your very detailed information and suggestions. Okay, so I think the very interesting takeaway from your presentation is that we found that offtake uncertainty is a kind of big risk for hydrogen business, right? So I think, yeah, rather than the technical issue, I found it's very interesting. So people think the offtake certainty needed for the hydrogen business. So do you have any idea from OECD perspective to resolve this issue? Or, okay.
I think if I have really well-established answer to this question, I probably became very successful entrepreneur by providing or tailored answer to offtake risk.
Yeah.
But I can share some of the key points that we found quite interesting and then somewhat working in our partner countries. One of the key issues that why offtake risk is present is about the price uncertainty. There's no merchant market that exists for the clean hydrogen at the moment, so it's very hard to tell how the price will change, how volatile it will be in the coming years. So that kind of gives a very uncertainty and then gives a challenge for the investors or developers to design HPA, which is hydrogen power hydrogen purchase agreement, which is similar to the PPA. So without that, it's for the investors, committing to offtake agreement is quite a bit of a challenge because you have also vintage project dilemma where when you lock in the projects now with certain price in 2023 or 4, but in coming 2-3 years you can forecast because all this discussion in the market, you can expect the price will go down. So you don't want to commit when the price is peaked. So a lot of market players we saw currently is waiting until the price goes down, or they accumulate some knowledge about how the price will go, or all this incentive package that is announced that we discussed exclusively today in details like IRA or European Union's current package. They want to see how it works. So that kind of gives a bit of the behavior pattern that we see that investors are waiting for the right time, they call it. But at the same time, from the public side or the more bird's eyes, we think it's very important to push forward this market to have a steep learning curve. So one thing we saw to mitigate the offtake risk is obviously to stimulate the demand in the market. For instance, we see the decarbonization mandate in Europe or the United States is quite working kind of effectively to make the market to understand how they can absorb or how they can consider the clean hydrogen in their business model. For instance, the statistic we saw from the European Union is the synthetic aviation fuel derived from the renewable hydrogen must make up the 1.2% of all aviation fuel, and 42% of hydrogen used by industry must be renewable by 2030. And this mandate, this number, will obviously make the investors or market players to work and how they can adjust their business model to be ahead of this regulation, because you will have penalty or you lose the competitive edge if you don't comply with this coming mandate or the regulation. The other factor we want to highlight is we're seeing very innovative market-based alternative or public procurement. For instance, we saw the recent auction successfully launched by H2 Global. That was a successful measure in terms of stimulating supply and demand, also gave some idea about how the price will look like. Of course, it was the first auction with a very limited number of projects, so this is a very slim data, but we are expecting after rounds of the auction, this auction is of course also replicable in different jurisdictions, thereby could pioneering how the market will go, can grow further, which can also contributing to the offtake risk mitigation. Last one, I want to highlight that public support is essential. If we look at the histories of how renewable technology has grown, of course, it's a bit of different nature of the market, but still, if you look at this kind of low carbon technologies historical growth, what has played significant role in the early stage was actually public support. Either it was feed-in tariff, or either it was incentive plan, or the tax credits that, or through the green stimulus package back in the days that worked so effectively to make the market have a boost at the early stage and grow further, which is also essentially can work with the clean technology like hydrogen to grow further and then mitigate the early stage kind of risks that they are facing at the moment.
Thank you so much. Okay, so thank you. Then Christian, so maybe you feel some jet lag. You just allowed it, yeah, like last night. So thank you, even for joining this forum. So I think your bipolar play works very innovative. I think actually I am very surprised you apply carbon for electrolyzer bipolar play. So, so how close is this technology to commercial application for PM electrolyzer?
So thank you for the question. I think it's very important to see this technology comes from our redox flow technology. We developed this material for redox flow in the last decade. So on the one hand side, we have really long experience how we can produce it on a larger scale, how it's reacting and what we can do with this. On the other hand side, we started the application for fuel cells a few years ago and now for electrolyzers last year. So on the one hand side, it's really on a low technological readiness level at the moment. We would say we have tested the components, something TRL 4 probably. For
TRL 4?
This is probably the status quo. We want to go to 5 and hope to make us the first stack in total of this and say, okay, this is a realistic environment. But this is for the electrolyzer. For the fuel cells, I think it's more from nowadays 6 going to 7 because we have tested it as a stack system nowadays. We can do this. We do this with industrial partners now. They are interested in this technology. And if you go back to the flow battery, now it's sold totally. And this is a good point. This is 9 TRL. So we get the information from the steps before, so we are faster today than we were in the past. But it will take some steps. So on the one hand side, it's very promising at the moment, but you know, you are also a researcher, there are always some hurdles sometimes you will see in the future, and we have to be really looking for this and make the progress step by step, and then I'm optimistic we will have really a product for the industry in the next years.
Next years for electrolyzers?
No, not next year, years, plural.
Okay. Okay. So if any Korea company interested in your technology, bipolar technology, so are there any ways for them to implement your technology to their products? Are there any ways they have license or how? Because currently, if they want your carbon-based bipolar plate for electrolyzer, technology is not there yet. Yeah, you need more works. So at this stage, if Korea company interested in your technology, so what can we do, or what are your suggestion for the company?
I think for each company in the world, as for Korean company, it's the same. I think it's an early stage at the moment, but most of the technologies we are developing at Fraunhofer will be done with industrial partners coming from a stage like this at the moment. 4 or 5, then we try to start with industrial partners. It's very important for us because then we get the right information, we are on the right way, that there will be really a product at the end and not that we will make a solution where there's no problem probably. So it's important to have these partners. And we have no limiting how we can act with the patents. That's a good
Okay.
point. It's always a question of the negotiation, but we have to keep in mind, for us it's important, it is good if we can hold the patent and give a license, so exclusive and non-exclusive license, limited to countries or non-limited, is everything is thinkable. But the good point is, if we are holding the patent and we are focusing on different applications, then we are doing from our own interests the next steps of modifying, improving the material, because then we can go to the partner again and say, okay, this is a good solution, for example, a new surface for flow batteries and for electrolyzers you are interested in, and so everybody of our partners can participate in the success then. If we sold it totally the patent, then it's burnt area for us. We can do nothing then. So there, it's very important. We try to make a very good licensing with industrial partners, but mostly, if possible, limiting to the application in which he is interested, really.
Okay, thank you. So, for example, in your cooperation model of individual orders, it's like work for others in your institute. So, when patents are issued during the project, who retains the ownership of the patent? The customer or developer? So, what I mean is that the customer to give you some funding for the project, and patents are issued during the project. Then who owns who retains the ownership of the patent? The customer who funding your work, or the developer?
At the end, both is possible. We have an example with a partner, in this case from China, then the patent is going to China in this case. It's a very special application we talked about, and this is very clear. We have other contracts with other partners where we are holding the patent at the end. We share the cost and give the license to the partner to say, okay, you can use it for this application in this area sometimes, because sometimes we have partners, they are not as big as, for example, so the big companies from South Korea, but smaller one. And if they are also interested, then we can make really an agreement to say, okay, you are focusing on South America, but that's it. And so it's possible that make it payable for them, and they are not able really to deliver the market of the whole world at the end.
Yeah. Oh, you are very flexible. I think. Yeah. Thank you. And finally, I think I am very interested in your low temperature co-electrolysis. So, would you give us some more detailed information? What is the Terra level? So when you do your co-electrolysis, you produce syngas, right? So would you give us more detailed information?
Our co-electrolysis from the project with the methanol is on the low temperature, lower than 100 degrees at the moment.
Lower than 100 degrees?
Yes,
Really?
we try to do this because of the material limitations there, but we try to go to this 100 bar level. That's for us important, to have the high pressure for the next step for building the methanol. So we are trying to make a high pressure, but not at too high temperature there. But this is at the moment under optimization, to be honest. It started early this year. It was in spring this year. So that we can't give the final results at the moment. You have seen this was the first test. It's a 5-cell stack at the moment. We tested it at our institute. Now we want to make the next step with a bigger stack there in Leuna. But there are not the final results at the moment because, as mentioned before, as mentioned all the colleagues, we are depending on funding. We need money all the day.
Yeah.
So we are not a governmental company. We need the money from the market. It could come from government, but we need the partnership with industrial partners, and therefore we get the contract from them, the money. And if this comes, then we can go always the next step. Without our partners, we are not able to do this because of lack of money.
Okay. So if you feed your with water and carbon dioxide to your cell, can you get syngas? If you feed to your cell with water and carbon dioxide, can you get syngas?
Well, I can get
Synthetic gas. Can you get synthetic gas by feeding the water, just water and carbon dioxide?
Yeah.
Can you get? Oh, really? That's amazing. Okay, thank you. Okay.
Thank you.
Then let's move to 손준혁 책임님.
안녕하십니까.
예, 안녕하세요. 지금 에멀슨에서 굉장히 그 좋은 기술을 보여주신 것 같아요. 사실은 이제 어떻게 보면은 그 IT 그런 그 테크놀로지를 이제 이 하드웨어에 접목시키는 굉장히 이제 중요한 일인 것 같은데, 이제 말씀하신 것 중에서 이제 디지털 트윈 말씀을 하셨는데, 사실 이제 저희가 이 뭐 수전회 쪽이라든지 그 디지털 트윈 연구를 해봤는데 이게 굉장히 복잡해서 사실은 이 디지털 트윈을 만드는 것이 저희 시스템과 하드웨어 시스템과 굉장히 유사한 디지털 트윈을 만드는 굉장히 어려운 기술이었었거든요. 근데 그럼 지금 그 에머슨에서 하는 그 성숙도 이런 디지털 트윈을 아까 한다고 하셨는데 그 성숙도는 어느 정도나 되나요?
저희가 그 작년이죠. 아스펜텍이라는 회사를 인수를 하면서
네.
이제 기존의 프로세스 인더스트리 쪽에서 공정 시뮬레이션의 역할을 많이 좀 지원을 했었고 거기에 대한 석세스를 많이 좀 이뤘기 때문에 그 기존에 있었던 프로세스 인더스트리에서 이제 넘어와서 지금 수전의 공정으로 넘어가는 과정에 대해서 좀 하이라이트를 하자면 과거에 지원했던 이런 기술력과 소프트웨어의 이런 완성도 때문에 수전의 시스템에 적용을 한 사례를 저희 내부적으로 판단하기로는 한 95% 이상의 모사도를 좀
95%요.
예, 이상의 모사도를 효율적으로 좀 낼 수 있다는 것으로 좀 입증을 하고는 있는데 현재 우리나라에서는 아직 적용 사례가 없기 때문에 많은 파트너스다 그리고 고객사들과 함께 프로젝트를 진행하려고 노력을 하고 있습니다.
근데 그게 이제 그 완성도가 95% 얘기할 때 그게 사실은 그 시스템의 사이즈에 따라 많이 달라질 수 있을 것 같거든요.
맞습니다.
작은 거는 어떻게 보면 좀 할 수 있지만 시스템이 커지면 좀 복잡하고 그럴 수 있는 어떤 시스템 사이즈에 따른 어떤 영향, 어떤 기술의 완성도가 좀 달라지는 건 없나요?
현재까지는 우리나라에서는 아직 파일럿 프로젝트들이 많이 진행되고 있기 때문에 아직 스케일업까지는 진도를 못 뺀 상황이고요. 물론 해외에서 아까 앞서 프레젠테이션에 말씀드렸던 뭐 캐나다의 성공 사례도 있긴 한데 거기에서는 저희가 주기계 설비 또는 메인 설비를 이제 컨트롤하는 역할까지는 디지털 트윈으로 구현을 하진 못했었고 대신 우리나라에서 진행되고 있는 파일럿 프로젝트에는 좀 적용을 해서 진행하려고 하고 있습니다. 그래서 아직까지는 뭐가 입증할 만한 이런 솔루션의 결과치가 있지는 않지만 뭐 대형 스케일업 과정에서 분명히 기존과 같은 파일럿 스케일의 규모와 같은 모사도를 낼 수 있을 거라 확신하고
네.
있습니다.
근데 이제 만약에 어떤 하드웨어 수전을 예를 들면 연료전지도 마찬가지지만 그런 회사가 이제 에머슨이랑 같이 이제 일을 하게 되면 사실 이 회사 갖고 있는 기술이 다 그쪽에 노출이 되거든요. 에머슨에 결국 소프트웨어라든지 그런 시스템을 만들게 하다 보면 이 갖고 있는 기술이 다 이제 그쪽에 인풋이 들어가야 되고 그다음에 그걸로 소프트웨어를 만드는데 그런 그 각 회사의 어떤 기술을 좀 보호해주는 노출되지 않게 지금 그런 어떤 구체적인 어떤 장치 같은 것들이 좀 있나요?
저희가 오늘 이제 프레젠테이션에 말씀드렸던 내용 중에 키 메시지는 이제 바운드레스 오토메이션입니다. 그래서 계기 단의 필드 디바이스부터 중간 단위의 컨트롤 시스템 그리고 뭐 상위 단의 클라우드 서비스까지 전 구간에서 에머슨 솔루션을 넣을 수 있기 때문에 물론 뭐 염려스러운 기술에 대한 누출 부분도 충분히 인지하고 있지만 특히 소프트웨어적으로 좀 설명을 드리자면 저희는 이제 소프트웨어 프로바이더 역할을 하고 있습니다. 그래서 고객사들이 또는 엔드 유저가 원하는 수치에 따라서 테스트를 하는 본인 고객사들이 온 아이덴티티 그러니까 기술력을 갖고 있는 것을 딱 존중을 하고 저희는 뭐 별다른 그 기술에 대해서 깊게 논의를 하기 위해서는 하진 않고 있지만 뭐 필요하다면 저희도 접근을 해서 논의는 하고 있고 특히 알고 계시듯이 NDA 같은 이런 협약을 통해서 진행을 하고 있기 때문에 특별하게 염려되는 부분은 없습니다.
네. 네, thank you again for all the presenters. Let's give them a big hand. Okay. So we'll wrap up this discussion session. Thank you.
네, 고맙습니다. 지속 가능한 청정 수소 프로젝트의 발전과 또 글로벌 혁신 촉진 방안에 대해 깊이 있는 토론을 나눠보았습니다. 네, 이번 시간을 통해서 각 분야 전문가분들께서 공유해 주신 인사이트가 앞으로의 발전에 큰 힘이 되기를 기대해 보겠습니다. 수고해 주신 좌장님과 또 세 분의 패널 분들께 다시 한번 큰 박수 부탁드립니다.